So our next speaker will set up the laptop, and it's Elliot Saba, one of the core developers of the Julia language. And the talk will be about BinaryBuilder number 2. So as all of you know, maybe not all of you, but actually many packages in Julia, they depend on some external libraries written in other languages. For example, plots.jl needs some plotting libraries written in other languages to be set up. And this all happens behind the scenes, very convenient for users. And BinaryBuilder.jl did it, and BinaryBuilder number 2 is even better, faster, cooler, and nicer, and Elliot will talk about it. Round of applause.
Thank you, Dimitri. All right, can't do this without this. For those of you who don't know me, I'm Elliot Saba. I'm Static Float on GitHub. I'm the blue whale with the Santa hat. This helps people to remember. So, welcome to my personal mountain that I have been moving for the last couple years. I call this talk BinaryBuilder 2, Return of the Compilers. Alternatively, Revenge of the Transitive Dependencies, or even Terror of the triply escaped wrapper script argument parsing. Now, just as a preface, for those of you who are not fully aware, BinaryBuilder is not a way to compile Julia code. So if you're here for this, this is your judgment-free time to get up and go to something else that's more interesting. Also, BinaryBuilder 2 is not production ready. But it is sufficiently developed to experiment with. And it's these kinds of experiments that I want to invite other developers to come in and help provide feedback, help shape the development of BinaryBuilder 2, etc. So I'm going to be showing off a lot of cool things that I've built and that kind of open up possibilities for the future. But it's not quite ready yet for us to integrate into Yggdrasil and start building everything with. OK, so let's start with what was wrong with BinaryBuilder itself. One of the big pain points, especially for our intrepid Yggdrasil maintainers, is that large projects like LLVM, CUDA, etc., have these torturous build cycles where we build some large project, we save that as a temporary JLL, we then use that as the input to a further build process that splits it apart into separate pieces. We have to make sure that the version numbers match across all these different pieces. If one piece fails, then we have to do all of the things over again so that the version numbers match across the entire thing. It's just a huge mess, and it's cataloged in this issue that's been open for literally years. Another big problem with BinaryBuilder is that what we call compiler shards, the pieces of the root-fs system that we assemble for the build environment, are very difficult to create. There's a lot of black magic that goes on in there. There's patching around of the GCC and glibc build processes just to make everything work as reliably as we want it to. And this makes it very difficult to add new targets, to add new ways of building things. There's been interest in having like RISC-V and WebAssembly and outputs for BinaryBuilder for a long time. And although these efforts made some progress, they're quite stalled out for years. So something needs to change here. And I blame this all due to the monolithic design of BinaryBuilder. It's this huge, towering stack of technology that goes all the way from containerization primitives up through building cross-compilers, and finally to like the infrastructure that bundles and prepares JLLs for preparation on your computer. So how am I going to fix this? Of course, a gigantic rewrite that takes years. How else would we fix it? More layers of indirection. The first thing is to break it apart into a more modular design. So instead of having one giant package, or since Mose was so upset with the pre-compilation times, he actually split it out into 2 packages. Now we have like 13 packages. But the cool thing about these packages is that they're useful in isolation. So for instance, the containerization primitive from BinaryBuilder has now turned into Sandbox.jl. The collection of wrapper scripts around GCC and Clang is now in its own BinaryBuilder Toolchains.jl. And that's a package that you can actually use outside of BinaryBuilder. So if you want to get a C++ toolchain on your local machine targeting some other machine, you can just ask for it, and it'll download a JLL, it'll jit out some bash scripts for you, and boom, you can just use it. We're also reworking the internals of BinaryBuilder to use these primitives that allow you to have a build flow. Say, build something, extract some pieces, wrap that up into a JLL, extract different pieces, wrap that up into a different JLL, etc. So things like the Clang build process, the CUDA build process should be greatly streamlined. And just in general, we're going to try and centralize more pieces of BinaryBuilder in one place so it's clearer how the whole thing fits together. Right now, there's like magic pieces of Yggdrasil that build GCC that then get written out to your local directory, and then you commit that up to BinaryBuilder. It's a huge mess. We'd rather just have binary things are JLLs. And when you want GCC for BinaryBuilder, you download GCC JLL. Everything should just be JLLs. So right now, these are some of the new packages that I have built that exist. They're even registered, although they're all pretty unstable. So don't, with the exception of like Sandbox, which has been around for a while, and JLL Prefixes also has been around for a while. I am going to talk about these and just give a brief overview, some quick demos of these things, and we'll kind of build up some of the pieces so that we can get our way up to BinaryBuilder 2. What is it? How does it bring all these things together? And what does it look like to use? So Sandbox gives us our file system and environment control. This is the containerization primitives I'm talking about. So it has a few separate features like nesting, so you can have sandboxes inside of sandboxes inside of sandboxes. You can have persistent overlay mounts. So that's how we do things like have a root FS system, like a base Debian image, and then you make changes to it. Those are stored in an overlay FS layer, and then you can leave that container, then come back to it to debug something that went wrong, and your changes are still there without actually affecting the root FS system on disk. It has bin format MISIC and QEMU support for multi-arch execution. Meaning, if you're on x86 Linux, you can run AArch64 Linux things. This is a possible potential hope for doing bootstrapping of foreign executables inside of BinaryBuilder. So we've always cross-compiled everything and have not had the ability to run things for the target inside of our build system. But in some cases, we may be able to. It's not something that we want to do every time, but in cases where we absolutely need it, it would be nice to have the option. And I'll show an example of this later. So Sandbox is it's basically a containerization layer for Linux guests. And it runs best on Linux, but it can also run on Mac and Windows through use of like Docker and Podman. It can kind of puppeteer those things to do what it needs to do. There's one glaring exception, which is these overlay mounts, which are kind of fancy. I have not yet figured out a way to replicate that using Docker and Podman. And because that's important for some like high-performance stuff we do in BinaryBuilder, BinaryBuilder 2 does not work on macOS and Windows yet. But I will probably implement a slow workaround for those things in the future so that it will work on Mac and Windows. OK, so I've talked a lot. This is going to be a veritable fire hose of information, but let's take a quick break for a demo. So Sandbox Demo. What does Sandbox look like? Is this visible to everybody? Is it too small? Let's make it a little bigger. Is that good? Great. So just a quick example of what do I mean by containerization? What is Sandbox? Here we say, OK, we're using Sandbox, and we're going to build a Sandbox config, and we want to mount a Debian root FS at the root of the container. And I want to mount a read-write directory, which is just going to sit right next to me in this directory. And we want this one to be read-write, not overlaid. And we'll define some environment variables just for fun. We'll hook up standard in and standard out, and then we'll just run bash. So if I run this Sandbox example, what happens is, boom, it drops me into a container, just like Docker would. And if I look around, there's some stuff here. I can do like apt update. You know, it does its thing. I can say like, OK, I want Vim. And it can write to the root file system, whatever. All these things are being stored in a temporary overlay file system. When I leave this, all those things are lost. However, if I go into the read-write directory, I can touch foo here. And over here, you'll see that there's a foo file here. I can edit it here on my host system. And then I come down here, and it's there, right? So bidirectional communication. This is how we save our JLL outputs. everything's good and happy. Oh, and just so you know, the things I said were true. There we go. Everything's demonstrated. Awesome. All right, so that's Sandbox. Any questions about this real quick? OK, good. I think actually we should probably save questions for later, because we need to do the microphone thing. So back to the keynote. All right, JLL Prefixes is for dependency collection. So one of the hard problems we have to solve in BinaryBuilder is getting all the JLLs that we need for our build. We need the transitive dependencies. We need to obey the compat bounds. And most importantly, we need to ignore the compat bounds that the Julia resolver would normally enforce based on the current running version of Julia. Because Julia itself has some JLLs that come with it. And usually, you would want to resolve, say, libcurl to the same version of libcurl that Julia itself has. So JLL Prefixes is basically a way to get stuff in the way that BinaryBuilder wants. It's not exactly that exciting. But the cool thing about it is that it allows you, as a user, to get JLLs, unpack them into a prefix, and then use them outside of Julia if you want to. This is how we unpack things like GCC, glibc, binutils, et cetera. So here, I'm going to download ffmpeg.jl. And what I do is I tell it, OK, collect me the artifact path for ffmpeg. So it resolves ffmpeg, it finds all of its dependencies, it collects all of the artifact paths, and gives me a list of paths. Then I have this thing that allows me to deploy it to a prefix. And that will either copy or hard link or symlink or whatever your operating system supports to put it all into a prefix. And then all the files are living next to each other, and we don't have to do any of the fancy shenanigans that we normally do in JLLs to allow libraries to find each other, because they're all sitting right next to each other. So if you wanted to, for instance, have ffmpeg available on your system, built by BinaryBuilder for whatever reason. You don't want to use apt-get. You just want to use the JLLs because you love them and you're a fanatic. You can do this. And you can unpack it into your bin directory somewhere, and it will just work. So you can see here, all I did was I just ran ffmpeg-version, and it has it here. It says, yep, I was built on an ARch64 Linux machine. Because right now this is running inside of a ARch64 Linux VM running on my ARch64 Mac OS machine. But we can go one step further. We can say, all right, Elliot, you said that Sandbox allows us to run foreign architectures. What if we were to collect the ffmpeg artifact paths, but for, say, an x86 machine, and unpack them, and then use Sandbox to mount in our ffmpeg directory and say, Sandbox, I want you to include the bin format MISIC hooks needed to interpret x86-64 on ARch64. And this all just works. So here, we run this example. And these examples are live on the BinaryBuilder 2 repository if you want to peruse them in greater detail. I know I'm going super fast through them. I'm mostly showing you that this stuff exists rather than going line by line in the code. And here, yes, when you ran version, it says, nope, I was built on an x86-64 machine. So very transparent, very easy to use, as long as you know the magic incantation, which is that extra little bit here saying, hey, I'm multi-arch, and the platform that I want to add is this foreign platform, which is this one, where I choose the architecture that does not match the one I'm on. All right. That's enough of this package, I think. Quick little side note. I've been using these platform objects. They're in base Julia, but BinaryBuilder, as usual, needs to do weird, unusual things, like talk about cross-platforms, where you have a host that's x86-64, for instance, and a target that's ARch64. The way we do this is we create a cross-platform object. And this cross-platform object encodes the target in the tags of the triplet. So you can see here, like, if I want to talk about a cross-platform object here, I have this string that says, oh, I'm x86-64 Linux, but I'm targeting ARch64 Mac. And by using this, the whole artifact system is able to deal with these cross-platform objects natively. So you're able to download and use artifacts for your local machine very easily. This is just a brief mention that these kinds of things exist. So when you see these cross-platforms, this is what it means. It means we want to run something that runs on Linux, but it builds something for Mac. And so when you want to specify a compiler or anything, you have to use these kinds of cross-platforms. For the internals of BinaryBuilder, that is. OK, let's build our way up to the toolchains. So BinaryBuilder Toolchains is a package that downloads GCC, it downloads binutils, it downloads the Linux kernel headers, et cetera. It unpacks them. It builds bash scripts to do argument parsing, like, for instance, disallowing setting the microarchitecture if we don't want to allow that, like automatically setting the sysroot, all these kinds of things that you don't want to have to deal with. There is some really interesting technical choices made here, such as Julia code that creates bash scripts, but the structure of the Julia code mimics the structure of the bash scripts. What I mean by that, I'm just going to show you, just so you can feel the insanity of what has to be done here. In the C toolchain here, we have these wrappers that we build for things like GCC. And so here we say, OK, here's the function that's creating a wrapper for GCC, and it's writing the wrapper out to I/O as it goes. And it needs to do things like check, hey, is the lock microarchitecture flag set in my toolchain struct? If it is, then I need to match all the arguments, all the flags that are being given to me. If any of the flags match this March thing, then I need to make an error. So the way you would normally do that in Bash is you have an if statement with like a regex compare, and then inside the body of the if statement, you would error out, et cetera. I don't want to maintain like 37 different variations of these same bash scripts. I want a way to generate the bash scripts. Well, what language am I going to use to generate the bash scripts? Of course, it's Julia. So what I do is this flag match like function that has a do block will create the if statement that does the regex compare here using my own like string macro thing here. And then inside here, I can just print out whatever bash stuff I want. And so all of these things are this like incredibly cursed mixture of Julia code that's generating bash scripts. End result is we have a slightly more maintainable way of creating these bash scripts that make the wrappers for the executables that we're going to run to build things in BinaryBuilder. All right. So right now, these tool chains, there we go. They only contain GCC and binutils and such. Eventually, we'll have toolchains for Fortran, Rust, Go, et cetera. There's still a work in progress, though. But the course is already plotted. We already have something that works kind of end to end for this stuff. The coolest part about this is that it's usable outside of the sandbox as well. So you can run this code, create a platform that goes from your host platform to your host platform, and then say run shell with a C toolchain and a host tools toolchain. Host tools toolchain is the thing that has like make, awk, grep, that kind of stuff. And then you can just say like pound cc, and it will have defined an environment variable that points to the wrapper scripts that it generated, and you can just use it. So let's see if I can put my money where my mouth is. This is where the demos get real dicey, because these toolchain examples are a little crazy. So by crazy, I just mean there's a lot going on. So if I'm going to get this running in the background. So this toolchain example will ask for a C toolchain and a host tools toolchain for the platform that I defined. It's going to call this with toolchains function, which gives me where the toolchains are unpacked, and also the environment block that needs to be applied, such that things like CC, LD, AS, et cetera, are all defined. Then, in a temporary directory, I'm going to spit out a main.c. I'm going to run cc-o main, blah, 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 main.c with this environment. And then I will actually run main. And here, it successfully said, hello, JuliaCon. If I wanted to, I could also do the run shell thing. So I'll just do that as well afterwards. I'll run shell on the toolchains. And by the way, all these like warnings and stuff, this is my patented system for remembering when I need to implement something later. So you'll see a lot of these. And that didn't work. Why did that not work? I need to save the file. That's why they pay you the big bucks. All right. Nope, that didn't work either. Let's look back at my slides. I think I had this in my slides. Huh. Oh, no, it did work. I'm in Bash. That's right. So, yeah, I have CC defined. That's funny. It's just it's reusing the styling because the PS1 and stuff is environment variables that got carried through. I'm not inside of Sandbox. I'm just inside Bash inside of Julia. So, so yeah, I have a CC here, and I can do CC, version, and it's GCC 9.1, which is the version that's coming from BinaryBuilder by default, et cetera, et cetera, et cetera. And I have like an AS and all that kind of stuff. OK, and I exit. Now I come out to my real Bash, and everything is good and happy. All right, real quick, JLL Generator is machine-readable descriptions of JLLs. So all the JLLs built from BinaryBuilder 2 now have a JLL.toml file, which is like the machine-readable way of saying what products are there, what license is it, what sources did it come from, what actual upstream version is it, et cetera, et cetera, et cetera. One of the nice things that it has is library dependency graphs. libfoo depends on libbar, which came from libbar.jll. The reason why that's important is because that enables the next package, which is the lazy JLL wrappers. This is kind of a fun place for people to suggest new ideas because we could have some really nice, rich metadata about JLLs here, things like SPDX software bombs or something like that. But the real reason I made it is because I want to load libraries lazily. And on Julia 1.11, if the whole subtree of dependencies has been built by BinaryBuilder 2, then we get lazy libraries for free, which is great. So libraries will not be loaded until the first C call. Probably the first things that we'll see this actually used for are the dependencies for Julia itself, because those will have the biggest impact. They'll cut down a little bit of our time to first, well, not time to first plot, but the startup time of Julia, because you won't have to load, for instance, OpenBLOS until you actually try to do a matrix multiply. OK, so that's my whirlwind tour of some of the packages that make up BinaryBuilder 2. I want to quickly say, for the users, build tarbos will remain relatively unchanged. There'll be a little bit of stuff that you have to move around. But like eventually, we're going to have Yggdrasil able to build both BinaryBuilder 1 and BinaryBuilder 2 builds. And we'll just slowly move things over to BinaryBuilder 2 once that support comes online. Let's really quick talk about the build flow changes in BinaryBuilder 2. So BinaryBuilder 2, to solve the problems that like LLVM and CUDA and stuff have, it now separates the notion of building, extracting, and packaging a piece of software. So you have a build config. You can call build on it. You get a build result. An extract config takes a build result and extracts things out of it. And you can run multiple extractions for a single build. So you could have like a build of a package that have an extraction that takes only the shared library and uses that with Julia, and another one that takes everything and uses that for BinaryBuilder. This is the idea behind separating out these two pieces. You could also have a build that builds all of LLVM, then separates it out into Clang, liblllvm, whatever other things that you build from LLVM. I'm not sure. A package config takes multiple extraction results, like across all the different platforms that you did these builds on, bundles them together, and creates a JLL from them. The build tarballs function does all this for you automatically. So 99% of people don't need to worry about this. For the people who need that extra bit of like, insane customization of their build, these nuts and bolts functions are available. The GCC build process, for instance, uses some of these things. I said all these already. Yep. Oh yeah, another example use case could be like you have a host-only tool like TableGen that you need to build once and then use in follow-on builds. So you could have that as its own build, and then the other builds can use it in later on steps. Another thing with BinaryBuilder that is very useful is universes. So sometimes you have a package that depends on another package, and you want to build new versions of both. Like you want to build a new version of libfoo, and libbar depends on libfoo, and you want to test them together. So you can add this -- universe flag on the CLI when you run your build tarballs, or there's also programmatic ways to do it. And this allows you to have them they live in the same registry, in the same depot, et cetera, so all the changes happen together. And then when you try and deploy it, if you specified a universe name, it will push it to a branch on your GitHub repository. So you can have multiple universes all in parallel for different things that you're testing. So if you're working on something, you specify the universe name, and it's very easy to access and share and use. OK, I have a little bit of debugging improvements here, but I'm just going to skip that because I'm running out of time. The BinaryBuilder 2 demo is actually the least impressive because it's basically just a build tarballs call, and it basically just proves that it works. So I'm going to skip that, and I'm going to go straight to questions because I'm running out of time.
Thanks. Round of applause. Thanks. Do we have a question? There. There, we have a question.
When you said that with lazy JLLs, you could avoid loading OpenBlast, for example, do you have like an estimate how much RAM and time we could save loading Julia if all of these things that it loads are lazy?
Yeah, it's not much. It's like, so back when we did the experiments, back in like the 1.10 or 1.9 time frame, I think it lowered the startup time from 120 milliseconds to 100 milliseconds. I don't remember how much memory it saved. There is a GitHub issue where we did those experiments, but we'll have to redo them because we have new versions of Julia now. But it's like a 10% savings, 20% savings, something like that. So it's something, but it's not a huge amount.
Thanks.
In the coming world of Julia C, what about binary building shared libraries with Python, R, MATLAB wrappers around them? Is that something that's a binary builder thing, or is that a separate issue?
Python wrappers around what?
Yeah, so you use Julia to write all of your serious high-performance code, but if you want to have impact and make your code usable to Python users, to R users, to MATLAB users, to say, here's this really cool new algorithm, the source code is all in Julia, but we want the entire world to be able to use it. Is there a pipeline yet, or thoughts about a design where we can build shared libraries with automated wrappers that get created for all these high-level languages?
Right, great question. So it's kind of the inverse of BinaryBuilder in a sense. Instead of bringing the world to Julia, it's bringing Julia to the world. I think the main difficulty there will be generating the Julia library for all the different architectures, because Julia itself does not cross-compile well. The Sandbox component can be useful for that, because with Sandbox, and I've done this before, you can build Julia for other architectures on that one machine. So that makes it easier. But there's a lot of questions about like the language bindings for Python, R, et cetera. I think that's going to have to be solved on a package-by-package basis, where we'll have we already have some interop packages. We'll have to work with each of the interop packages to figure out the best way to do that.
Nice. So we have time for one small question. Yes?
Yeah, hello. So if I want to execute a thing from a JLL, an executable, without going through the JLL, so just directly execute it from bash, what do I have to think about? Like, I don't have the ability to run any arbitrary Julia code before executing it.
Yeah, you need to use JLL prefixes to unpack it and all its dependencies into the same prefix. And you may need to set some environment variables depending on the JLL package. Many don't need any environment variables, but for instance, Git does.
Will the environment variables be encoded in the new JLL.toml then, so I can only use that as the source of truth, or where would I find that?
It's something I've thought about. Let's talk about it at the BOF this afternoon.
Great.
Thank you all.
Nice. Extra round of applause. Thanks. It was a really great talk.